and after that in detail about voltage series feedback amplifier. So I've completed voltage series feedback amplifier. Like we have seen what are the changes in the voltage series feedback amplifier in terms of overall gain, in terms of bandwidth, in terms of input impedance, output impedance, and all that. Okay, and before that, you should also know the different types of feedback amplifier. Like I have already shown you the different types of feedback connections, right? Like voltage series, voltage shunt, current series, and current shunt. So I'm going to show you about the other feedback amplifiers. Okay, but they are not in detail. You have to just know what is a voltage shunt feedback, what is current series, and what is current shunt. Okay. So to start with, let me take first voltage series feedback amplifier. This already you know. So as I told you, in the voltage series feedback amplifier, so first term indicates what you are taking, what type of feedback you are taking, whether you are taking a voltage signal or you are taking a current signal. That is the first term. The second term indicates how you are feeding that to the input source, whether you are feeding in series or you are feeding in parallel. So only that I am going to tell you about all feedback amplifiers. So this already you know, but just it is a recap for you. Voltage series feedback amplifier. Okay, so the voltage series feedback amplifier. So this is the amplifier part, and this is the feedback part. And as you can see, in case of voltage series feedback amplifier, I'm taking the output voltage. So always the output voltage has to be taken. It is not only output voltage has to be taken always parallelly. So from the output I am taking the voltage parallelly, and we have denoted the output voltage as V0. And since you are connecting the feedback signal in series, whenever you are adding the signals, whenever you are adding the signals in series, always they have to be voltage signals. Only voltage signals you can add in series, and when you are adding current signals, always they have to be in parallel. Okay, now what I'm doing, from the output I'm taking the voltage signal, and that voltage signal is VF, that is your feedback signal. So how much of the voltage signal you are taking? Beta times V naught. So beta indicates what amount of V naught you are taking. So VF, so feedback signal is VF, because I am taking voltage from the output. Now VF is a voltage signal. Now as I told you, when a feedback signal has to be added with the source and the feedback signal both have to be voltage. Okay, so voltage feedback signal has to be added with a source which is also a voltage. So that is how we take a series connection here. In case of so please keep this in mind. At the input, when you are combining the signals, so when you are combining the signals, if you are combining voltage signal, then that forms a series connection. When you are combining the current signals, that forms the shunt connection. So here it is voltage and series. So at the output I am taking voltage. Series means at the input the feedback signal has to be connected in series with the input source. So since the feedback is voltage, okay, and since the connection is series, the voltage source has to be voltage. So the source has to be a voltage source. This is what is important for you to understand. And amplifier. Now coming to what is the gain of the amplifier. You all know what is the gain of the amplifier. Gain of the amplifier is the ratio of output divided by input. Now for this amplifier, the output is voltage, and what is the input? What are we adding at the input side? We are adding two voltage sources. So the input is also a voltage. So for voltage series feedback amplifier, the gain is the ratio of output voltage to the input voltage, what we are feeding to it. So this is about voltage series feedback amplifier. Now you can understand this concept in a better way if I tell you about other feedback connections also. See here. This is a voltage shunt feedback. Okay. So voltage shunt means first term. Voltage means from the output I am going to take a voltage signal for feedback. So at the output I am going to take the voltage signal for the feedback. Okay. So I am taking V naught. So you can just see here I am taking V naught. So what is the feedback factor? It is beta into V naught. I am taking V naught. Beta into V naught. Fine, because it is voltage. Now the other part says it is a shunt, voltage shunt. Shunt means what? In what way the feedback signal is connected to the source. So shunt means you are going to connect in parallel. Now, as I told you, if you are connecting two signals in parallel, they have to be always current signals. When you are connecting two signals in series, they have to be voltage signals. Now you are connecting two signals in shunt. Okay. So at the input, if I am going for shunt connection, my source has to be a current source. Okay. So that's why the previous case, because it was series connection, I had Vs here. Now it is shunt connection, that's why I have here Is. Please understand. So from the output I am taking voltage signal. The part of the voltage signal what I am taking is beta times V naught. And since this has to be connected in shunt with the input source, when you are going for shunt connection, only you can go for currents. So the input source is a current source. And coming to the feedback signal. Now the feedback signal has to be connected to the input source. Yes, because you are going for shunt connection, input source is a current. So the feedback signal also has to be a current source. Only then these two current signals can be added in shunt. So we denote the part of the output signal what we have taken beta times V naught as IF. So IF is IF is the feedback signal, and now I am feeding IF in parallel to IS. So at the input, IS and IF are combined. IS and IF are combined. This is voltage shunt. From the output, I am taking voltage, that is beta times V, because at the output, I am taking voltage signal V naught. Part of the V naught is beta times into V naught. Now it has to be connected in shunt. So shunt means I can only go for adding in parallel. So when you are adding parallelly two signals, they have to be always current signals. So the source is the current source and the feedback is the current feedback. So IF is equal to beta times V naught. And coming to the gain of the amplifier. Now here the gain changes because it is a voltage shunt feedback. The gain, gain is the ratio of output voltage divided by input voltage. Output voltage is V naught, but input, what are you getting to the input of the amplifier? At the input side, there is mixing of two current signals, IS and IF. So if you remember your the concept of feedback after mixing, the mixed signals are applied to the amplifier, right, to form the input. Yes. So IS and IF are combined to form II. So the gain of this amplifier is V naught divided by II. So what is V to I? It is a resistance. Fine. So this is about voltage shunt feedback. Now coming to current series feedback. Okay, so current series feedback. So just analyze the first term, current. Current means what? In case of feedback, as I had told you earlier, the first term indicates what type of signal I'm taking from the output. Now it is current, right? So I have to take from the output current. So as I had indicated V naught as the output voltage, here current is I naught is indicated as the output current I naught. Now I have to take I naught. And what is the feedback factor? Beta. So what portion of output I am taking? Beta times I naught. I am taking beta times I naught. Okay. Now one more thing I told you. When you are taking the voltage signal from the output, we take it parallelly. So you can just compare the previous circuit. See here, in case of this is voltage series, right? The first term is voltage. So you can see the voltage is taken parallelly. The second series also voltage shunt. So because I had voltage, the voltage is taken parallelly. And here I'm taking currents. Can you see the series connection? So this is the series connection. So current has to be taken in series from the output. Okay. So what this is your output current I naught, and what portion of output current I am taking for feedback? Beta times I naught. Okay. So this is the first term. What is the second term? Second term indicates how we are connecting the feedback signal to the input source in series. I'm connecting the feedback signal in series with the source. Now, as I told, when you are connecting the feedback signal in series with the input source, the series can be only the voltage signals. In series, you can add only the voltage signals. Okay, so beta times I naught now becomes VF, because I'm going to combine the uh, signals in series. When you are combining the signals in series, they have to be only the voltage signals. So beta times I naught becomes VF, and since I'm going to add in series, the source also has to be VS. So only I can connect mix at the input Vs and Vf, where Vf is beta times I naught. So you can see here this is a series connection. Now coming to what is the gain of the amplifier. Now what is the gain of the amplifier? The output of this amplifier is I naught, because I am taking I naught from the output. And what are you feeding at the input to the amplifier? The mixing of Vs and Vf, which forms your Vi, which forms your Vi. So it is ratio of output current divided by input voltage. So you call this as conductance, the inverse of resistance. Resistance is V by I, and I by V is conductance. So this is what is about current series feedback amplifier. Only this, if you know, that is sufficient. So what is that we are taking from the output, whether it is current or voltage, and what portion we are taking? Beta times. If it is output voltage, V naught. If it is input voltage, if it is output voltage, V naught. If it is output current, it is I naught. And how we are feeding? If you are feeding in series, so the source and the feedback should be voltages. If you are feeding in current, the source and the feedback should be currents. Okay. So this was about current series feedback. So the last one is current shunt feedback. So current shunt. What is the first term indicates? We are taking from the output current signal. So first term is current. So from the output I am going to take current. So the output current is indicated as I naught, and the feedback factor is beta. So from the output source, from the output I am taking part of the current. So that is beta times I naught. Fine. So beta times I naught has to be fed as what? Shunt. So when you are at the input, when you are combining the feedback signal with the input source, you are going for shunt connection. When you are going for shunt connections, I can have only the current signals. That means our source has to be current and the feedback signal also has to be current. So this forms IF, because I am going for shunt connection. So this IF is fed here and you have IS. So here IS and IF are combined, and that forms II. So this II is given to the input to the amplifier. Okay, so current shunt feedback, I'm taking current signal from the output. Part of the current signal is beta times I naught, and how I am connecting at the input in shunt. So when you are going for shunt connection, both the input source and the feedback has to be current signals. So beta times I naught becomes IF, and we have the current source IS. And these two are combined to form II, which is given as input to the amplifier. So what type of gain we get from current shunt feedback? Current gain. Because gain is the ratio of output signal to the input, right? What is the output? I naught. And what is the input to your amplifier? It is II. Both are current. So you get current. So these are about the four different types of feedback signal. In voltage series, the gain is voltage gain, output voltage divided by the input voltage. In case of voltage shunt, it is output voltage divided by input current. So it is resistance. In case of current series, it is output current divided by voltage. So it is conductance. Next, in case of current shunt, is output current divided by input current. So it is current gain. So let us combine. Let us see the summary of all these four connections. So you can see here the same thing, whatever I have shown here, same thing is being tabulated. So voltage series, it is output voltage by input voltage. Voltage shunt, output voltage by input current. Current series, output current by input voltage. Current shunt, output current by input current. And these are all the feedback. Okay. So because it is voltage series, we are feeding Vf. So that is beta times V naught. Here I am feeding If, which is beta times V naught. And here current series I am feeding Vf, which is beta times I naught. And here I am feeding If, which is beta times I naught. So this is without feedback. With feedback, so you can see here without feedback there is no Vf signal, so I don't get Vs into consideration, so it is just V naught by Vi. If you consider feedback, it is V naught divided by Vs, where you know what is Vi, Vs minus of Vf. So same thing is been tabulated here. With feedback, the gain becomes V naught divided by S. Here with feedback, the gain becomes V naught divided by Is. Here I naught divided by Vs, I naught divided by Is. So if you just know what are the parameters I'm taking from the output, how you are combining, and what are the gains, that is sufficient. Only for voltage series feedback amplifier, you need to know about all the derivations, like what we derived, how the gain reduces, how the input impedance increases, and how the output impedance reduces, and how do you establish the gain stability. So this was about all the four types of feedback amplifiers and the comparison of the gains. So this was about the concept of feedback. Okay. You have come across two types of feedback here. One is the negative feedback, and that gives rise to amplification. Okay. And the other one is the positive feedback that was giving rise to oscillations. Okay. And you have also come across the working of an oscillator and what are the conditions to be met for the circuit to produce sustained oscillation, and you have also come across the different types of oscillators. Okay, and as per your syllabus you have studied about the RC phase shift oscillator and the Bean bridge oscillator. Okay, Now the next part of this module is the details about an IC called as 555 timer. Okay, so this is an integrated circuit. The name of this integrated circuit is 555. I'll tell you why it is called as 555, and usually we call this as a 555 timer. There is a reason why we call this as timer, because it is used for generating time delays. So it will maintain where we use this wherever timing is required. Say for example, if you are doing a work, okay, and you will set up the timing. So you will be checking what is the work done for the whatever time limit you have kept. Okay, so that is about the timer. So it is this IC is about the timing. That's why we call it as timer. For example, you take your washing machine or oven. For everything, you need to keep some timing. So you can use this IC where the timing is important. That's why I say this is used to provide time delays. Okay, this is used to provide time delays. So here what you are studying, you are completely studying about this IC, what is the internal structure of this IC, and how this IC can be used. How this IC can be used. So before going to how this IC can be used, let us have a small introduction about how it came into picture, and since it is an integrated circuit, how many pins it has, and details of every pin, and what are the basic applications of this IC. So let me introduce that. Okay, so as I told you, to start with, this IC is a timing circuit which generates the time delays. Okay, and this IC can also be used to generate oscillation. So I can say this will also provide oscillation. And how, when did it come into picture? It was introduced in 1971. Now you can see, and you have here what is the name of the company, Signetics. So they introduced this IC in 1971. Now it is 2020. Still, we are using this IC because it is so popular because of various reasons. The reasons why it is popular is because of the low price, okay, and ease of use. So you can use this timer easily for any application, and this IC provides good stability. Okay, so because of these reasons, still the IC is uh, used by the large mass. Okay, and what actually this timer IC is made up of? So this IC, when I say IC, that's why we call this as a package. Okay, so this IC is made up of 25 transistors and 2 diodes. When you go into the IC, look into the IC, it has 25 transistors, 2 diodes, and 15 resistors. All this on a silicon chip, and it all depends upon the manufacturer also. Okay, so how this chip is available? The chip is available as a dual inline package. Dual inline package means, so you'll have an IC with two sets of with 2 lines with 4 pins on each side. Dual inline package. Okay, so I'll show you how this IC is available. Fine. And coming to, I told you why it is called as 555 timer. There is some reason for it. The reason is this IC has 3 5 kilo ohm resistors in it. That's why they have just named it as a 555 after the this 5K resistors. That's all. There is nothing else. Okay. Because of this 5K resistors, it is just named as a 555 timer. Okay. Now, what are these features important? I have just uh, listed here where only some of the features. If you want to know about the details, some more details of the features, you have to go to you have to get the sheet, the data sheet of this IC, which is provided by the manufacturer. So you will have the complete details about the IC, how to use and the different configurations. So here I'm going to just list some of the features. So one feature is what is the power supply requirement for this IC to work. Okay, so if this IC has to work, it requires voltage ranging from 5 volts to 18 volts. So in this range 5 volts to 18 volts, any voltage you give, the 555 timer will work. And this 555 timer supplies 200 milliamperes of load current. Now you should know, along with this is the voltage requirement, and it can supply 200 milliamperes of load current. So if you connect anything to the timer IC, so it can drive that by providing 200 milliamperes of current. And when it is working, when the timer IC is working, what is the maximum power dissipation it can produce? It can produce the maximum power dissipation of 600 milliwatts. And all electronic circuits, okay, they are all temperature dependent, right? So the operating temperature of this IC is 0 to 75 degree centigrade. Okay, so above 75 degrees centigrade, I think you can't work on this IC. So there should be some fixed temperature. Above this, you can't work. Okay, and the duty cycle of the timer is variable. I think I don't know whether you know about the duty cycle. Whenever you go for timing, so whenever something is dependent on the timing, that is when the for what period, when some operation is dependent upon the timing. So in the time you have something called as on period and off period. Like for example, you have connected something to this electronic circuit, some external device. Now we have designed such a way that whenever time is on, the device will work. Whenever there is off time, the device will not work. So you have in the timing the T on period and T off period. So the duty cycle is nothing but ratio of the on period to the sum of on period plus off period. So on period is nothing but the period for which the device will get activated or something like that. Off period is one for which the device will get deactivated. So it is something like this. So I can say this as the on when it is active, and this is off because it is 0. So when it is inactive, so this is on and this is off. So the ratio of on period to the complete period, that is the sum of on period plus off period, we call this as duty cycle. So the duty cycle of this timer is variable. You can vary. These are some of the features of a 555 timer. Some more details can be got from the data sheet. Okay. Now this is where I'm going to show you the IC. As I told you, it is available as a dual inline package DIP 8. So 8 pins. So you can, here you can see practically this is how you get the timer IC. Can you see here? This is the IC with dual inline package. So you have 4 lines here, 4 pins on this side and 4 pins on the other side. And this shows the pin diagram of the 555 timer. So it has 8 pins. So here you can see, here you have a notch. So the importance of notch is the first pin starts from the notch. So this is your first pin, ground pin, and this is the second pin, we call it as the trigger pin. Third pin is the output. Fourth is the reset. 8 power supply. 7 is the discharge. Sixth pin is the threshold, and fifth is the control voltage. Let us see what is the importance of all these pins. Ground you all know. So it is very much important for any electronic circuit to have the ground. So whatever voltages we measure, okay, so for all that ground is important. All voltages what we measure is with respect to ground. And if this pin has, if this IC has to work, as I told you, the requirement, voltage requirement is plus 5 volts to 18 volts. So to which pin of this IC are you providing this voltage so that it works? You are supplying to pin number 8. Okay, so if this IC has to work, the voltage what you supply is through pin number 8. Uh, and from this IC, where do you get the output from? We get the output from pin number 3. I think you can just connect this with your op amp. Like you already know about the op amp. So op amp has how many pins? Where are you giving the input and where are you taking the output? Similarly, even here, I'm grounding the first pin, pin number 1, and what power supply this pin requires, I'm giving it to 8, and the output from this IC, I'm taking it from pin number 3. Okay, and I'll tell you about the other pins also. So let me tell about the other pins in details. Yeah. So pin number 1 is the ground terminal. So all the voltages are measured with respect to ground. That's why we require ground terminal. And I've told you about the supply voltage where we are giving and where is the output. Okay. Now, if I go in detail about the pin diagram, I think you should know beforehand what are the what are the details of 555 timer. This is the internal circuitry of the timer. This is how your timer looks inside. Okay, so if you know this, I can connect this with the pin diagram. So each pin, where are we taking? This is the internal circuitry of the timer, and you can see here each pin where it is connected. Okay, so first let me talk about the internal circuitry. Then we'll relate this internal circuitry with the pin diagram. Okay, so in general, I'll just tell you in brief what is available in the timer. So coming to the first part here. Yeah. So this is a voltage divider network. This is the voltage divider network. And you can see here, to this network, we have connected VCC, and that is to pin number 8. Okay. So this VCC is divided using this voltage divider network. How this VCC is divided? So at this point, you get 2/3 of VCC. This voltage is divided. 2/3 of VCC is available at this point. Okay, I'm sorry, not at this point. Sorry. So this is the voltage divider network. Okay, so at the first resistor you get 2/3 of VCC, and that is connected to the non-inverting terminal of this op amp. These two are op amps. Okay, let me come from the beginning. So you have this potential divider circuit which divides the voltage. What voltage it divides? It divides the voltage that we are giving it to pin number 8, that is VCC. So this VCC is divided into two voltages. One is 2/3 of VCC, the other one is 1/3 of VCC. Fine. So your VCC is divided into 2/3 of VCC and 1/3 of VCC. Now coming to the second part. So this second part here, you have two op amps. Can you see? So this is one op amp and this is one op amp. Now how are these op amps acting? They are acting as comparators. So you already know because in applications of op-amps, I've told you about the comparators. Okay, so the op-amp will compare the two voltages what we give to the non-inverting terminal and the inverting terminal. So these two op-amps are acting as comparators. The first one we call it as comparator 1 and the second one we call it as comparator 2. So the voltages what we get from this voltage divider network, that is 2/3 of VCC and 1/3 of ECC, these two form one of the inputs to this comparator. Okay, so this 2/3 of VCC is given to the non-inverting terminal of the first comparator, and this 1/3 of VCC is given to the non-inverting terminal of the second comparator. Okay, so here for comparison, one input is 2/3 of VCC and the other input is this control voltage to the comparator. Fine. One is the voltage what we get from this voltage divider network, 2/3 of VCC, and the other input is the control voltage. And even here, the second comparator compares 1/3 of VCC with the trigger input. Okay, so this is about the comparator. So the next part of this circuit is the flip-flop. I think this I have to tell you because this comes under module 5. So I'll tell you about the flip-flop there. Now as of now, I'll just tell you flip-flop is a sequential circuit. So you all know digital circuits are of two types. One is the combinational circuit, other one is a sequential circuit. So I can say flip-flop is a sequential circuit. Fine. So what is the difference between a combinational circuit and a sequential circuit? Combinational circuit, the output depends only on the present input, whereas sequential, the output also depends upon the past, right? That's why we say they have memory. So you just understand flip-flop is a sequential circuit. Okay, it has two inputs. It has two inputs. Okay, so the inputs to this flip-flop are one we call it as the set input, the other one we call it as a reset input. So what do you mean by the set input and what is the reset input? Whenever we give input, whenever we give input to the set, the output of the flip-flop becomes 1. That means we say the flip-flop is set. So, and whenever we give input to the reset, the flip-flop will reset. That means the output of the flip-flop becomes 0. Now, when this flip-flop enters into set state, when this flip-flop enters into reset state, that means when this flip-flop is going to give me 1 output, when it is going to give me 0, it entirely depends upon the outputs of the comparator. So you can just see this set is getting the its input from the comparator 1 and this reset is getting its input from the comparator 2. So these two comparators, after comparing, they can either set the flip-flop or they can either reset the flip-flop. Okay, so if comparator, when these two are comparing, and comparator 1 gives a high output and that high output is given to set pin, the flip-flop will give me 1. The output of the flip-flop is 1. And out of these two comparators, if comparator 2 gives us the high output and that will go to the reset pin, the output of the flip-flop is becoming equal to 0. Okay, in turn, the output of the flip-flop is going to the output stage. So this is how we get the output. So output is also dependent upon the flip-flop. So you can just see here, if it is 1, then the output follows whatever is here. And if the output of the flip-flop is 0, it is connected to the output stage, the output follows that. And coming to and other the next part. So I've told you about the voltage divider part and the two comparators and the flip-flop and the output. Next you have a transistor here, which is also getting its input from this flip-flop. Actually, this transistor, we call it as a discharge transistor. So when you are using this IC practically, we will connect this transistor to a capacitor so that uh, there is a path for the charges to get discharged. So this transistor is a, it is for discharge, where we connect a capacitor for discharging. Now when this transistor will get discharged, you can just see here, whenever the output of the flip-flop is 1. So this 1, whenever the flip-flop output is 1, you can see that is getting connected to the base of the transistor. You all know about the transistor as a switch, right? So you can control the action of the transistor as a switch by controlling the input what you are giving it to the base. This you already know. So whenever I am giving a high input to the base of the transistor, it enters into saturation mode. Whenever I give a low input to the base of the transistor will enter into cutoff mode. This already you know. So whenever the output of the flip-flop is 1, that 1 is given to the base of the transistor. So this transistor enters into the saturation mode, and that's how the capacitor will discharge. Whenever the transistor is in saturation, the capacitor will discharge. Whenever the output of the flip-flop is 0, it will drive the transistor into cutoff. It will drive the transistor into cutoff. Now the capacitor will start charging. See this importance of this charging and discharging. I'll tell you when I'll tell you about the working of 555 timer. So as I told you in the first slide, the timers are used for various applications. So one of them is it can be used as a multi vibrator. When I talk about that, I will tell you what is the importance of this charging and discharging. So as of now, you please understand. So this transistor, either uh, this transistor, either it will enter into saturation or cutoff, and the capacitor connected to it, either it will discharge or it will charge. Okay. The next you have another transistor here. Okay, to which we are connecting a reset. Now, whenever this complete IC has to be reset, then we'll give a input to this reset pin so that the whole IC becomes reset. After that, you can start working with this IC. Fine. So this was about the details of 555 timer. I think with this, now if I tell you about the importance of all these pins, okay, of this IC, you'll be able to understand it. So I think as of today, I'll stop here with the details of 555 timer. The next class, I'll tell you about the various pin details and the rest of the details related to 555 timer.